Hello folks, so in this set of videos we're going to go through chapter 14, which is kinetics. This first video we're going to talk about what exactly is kinetics and some of the ways it's measured. Then in another video we're going to go through the difference between differential rate law and integrated rate laws, how we can use them and how they're interconverted. And then we're going to look at some of the more advanced aspects like the relationship of temperature and kinetics in the Arrhenius equation. And finally, we're going to look at mechanistic determinations using kinetics. So we'll go ahead and get started. Chemical kinetics. Okay. So the idea here is that while stoichiometry can be used to predict how many products we should expect to be formed in a reaction, that has no bearing on how fast this will occur. It's all well and good to say this should happen, that this is predicted by spontaneity, this is predicted by and this is exothermic, this is should happen, but it doesn't say whether this will happen in 10 seconds or 2 million years. And that is what kinetics can tell us. Kinetics is essentially reaction speed or reaction rate. So some reactions are instantaneous, some reactions take a long time, like coal turn into diamond or diamond turning into coal. Those are not easily predicted by just stoichiometry. So we are going to measure reaction rates, basically the speed at which a reaction occurs in, say, molarities per second or atoms per second, or some sort of basically unit of measuring atoms over a unit of time. Now, before we get started, there are a few easy things we can do to affect the reaction rate. Obviously, the easier it is for a reaction to mix, the faster the reaction will occur. So physical state has an effect, because the larger the surface area, the greater the mixing. Solids don't mix themselves usually, so you have to shake them. Liquids will slosh around, but gases will react faster than most other things. They'll have spread out even more. But if a liquid, for example, is immiscible, so we have two layers, they can only react where those two layers meet, and so those have to be stirred together. Now, obviously, the nature of the reactants themselves, how stable they are. The more stable the reactants are, the slower they're going to react. Things like radicals are very unstable and they react very rapidly. But if you have a very stable compound, it takes a lot of energy to break bonds. The other major thing is concentration. Greater concentration, usually greater the reactant speed, because the more likelihood that molecule A is going to bump into molecule B depends on how many molecule Bs you have floating around. Now, in terms of temperature, that's another thing we can easily control. In general, there is a saying essentially that for every 10 degrees Celsius, reaction speed typically doubles. That it's a hard, fast kind of rule. It's not perfect, but for most cases, reaction speed usually doubles at every 10 degree difference. Because essentially the atoms are moving at a higher speed. They have higher amounts of kinetic energy at higher temperatures. The faster they're moving, the more mixing they do, the more likelihood when they collide, they break bonds. And finally, catalyst. A catalyst can greatly speed up a reaction. We'll talk about what a catalyst actually does a little bit later. But largely anything that can increase the amount of collisions of atom on atom will increase the reaction rate. So, first, how do we measure rate? Rate is just a speed of a reaction. It's measured as a amount versus a time. And the most common unit says molarity per second. So how many molars are decreasing per second? Now, speed, for example, is basically a directionless velocity. Well, a rate, much like velocity, needs some sort of direction. Are we speeding up? Are we slowing down? So we are going to look at a rate with a positive or negative units. So having a positive rate means something is increasing. A negative rate looks at the decrease of a unit. How fast is this decreasing? How fast is that increasing? So you can look at speeds relative to each other. We look at the reactant going away as the product coming in. We can look at relative rates of different molecules at the same time. But so, if we look at this general reaction, the kinetics show, the stoichiometry shows 2 A's going away and 1 B coming in. Now, this doesn't necessarily tell us how fast, but generally speaking, every time this reaction runs one time, 2 A's go away, 1 B goes in. And the amount of B we can form depends on how much A we started with. So we see a reaction that, if we looked at the concentrations of each guy versus time, would see a graph that looks something like this. That, for example, at 20 seconds, after 20 seconds, the concentration of A has decreased by 0.03. The concentration of B has increased by from 0 to 0.015. So it took 30 millimolar away and put 15 millimolar of B in. And then we drop, after 40 seconds, it dropped from 0.02 to a little bit under 0.01, where it dropped by about 10 millimolar, and this has been increased by about 5 millimolar from that. And we see as A approaches 0, B approaches the asymptote, which would be essentially 0.025 molar. Now we can see the relative rates of each one can be described by this simple equation. The rate of A versus the rate of B. A generic rate. As B goes in, as B comes in. And A goes out twice as fast. And so to make them equal, we have this 1/2. So A is going out twice as fast. So if A is going out 2 per second, B is coming in at 1 per second. Please note, in the future, when we refer to concentrations, an easy way to show a concentration is by having the chemical formula in brackets. These brackets say the concentration of A versus the concentration of B. And do not forget the delta. Delta simply means the change. So reading that formula that says the rate equals negative 1/2 times the change in A, the concentration of A over changing time, and that is equal to the change in the concentration of B over changing time. So A is decreasing, so that have a negative change. The negative sign makes that positive rate. A is decreasing by twice as much as B at a given time, and so that 1/2 helps make these relationships equal. Now let's take a different reaction, that A breaks apart into B and 2 moles of C. So in this case, A is being consumed, B is being formed at an equal rate, and C is being formed at a double rate. So we have a nice little graph like this. See, as A decreases approaching 0, B essentially comes in and replaces it, approaching the asymptote of 0.05. Now C will be approaching the asymptote of 0.1, double that of B. And so we can relate these two by a simple formula that the rate equals negative change in A over change in T equals positive change in B over change in T. So the rate of A and the rate of B are directly opposite, just by signs. But the rate of C, since it's double that, is equal to 1/2, is twice as big as A or B, so we need that 1/2. So when looking at relative rates, we can make this simple generality based on the stoichiometric relationship. That for any reaction where A with a coefficient of little a goes to B with a coefficient of little b, we can say the relative rates are equal to the rate of one over its coefficient, and that's equal to the rate of the other one over its coefficient. This is the one time where we will directly look at the chemical formula for this chapter. As we will learn later, we cannot assume too much about this chemical reaction. We know that every time 1A goes away, it forms B and then 2C, but how it does that is not directly obvious based on this chemical reaction. But we just know whenever 1A goes away and this reaction turns over one time, the byproduct is 1B and 2C. But from this, we can figure out the quantity of all compounds and the relative rates of all compounds as long as we can measure one of those two compounds, or one of those mini compounds. In fact, we often use things like light absorption properties to help us. So measurement of light absorption using Beer's law will help us. Beer's law simply states that the absorbance of light is proportional to the molar absorptivity times the path length L times the concentration C. So if even one reactant or product absorbs light at a specific wavelength, and the other guys do not absorb very strongly or much at all at those wavelengths, we can completely study this reaction. That we can see, as A is going away at this rate, that means B must be coming in at this rate. That C must be coming in at this rate, just because we know the rate of A. So, looking this over, for a reaction, 5 manganese 4 oxides plus 4 protons reduces the manganese to 3 manganese 2 pluses and 2 permanganates, so that get oxidized and reduced, and you form 2 water as the byproduct. So manganese oxide essentially disseparates, oxidizes, and reduces to form this. And if we look at the rate of consumption of manganese oxide being 20 molar per hour. So that after 1 hour, 20 molar has gone away. So is negative 20 m per hour. What is the rate of proton consumption? What is the rate of manganese production? And what is the rate of permanganate? So I'm going to write this out real quick and we will do that. It is relatively easy. This is relatively easy. I'm just working this out. This is the easiest part of this. We're not always blessed with something so easy. So with this in mind, the generic rate is going to be equal to negative 1/5 times negative 20 m per hour. The generic rate is going to be a rate, the reaction turns over essentially 4 m per hour. That's our generic rate. Well, this rate is also equal to negative 1/4 delta H plus over delta T. So if we know this is equal to 4 m per hour, we know that the rate of H plus consumption is equal to negative 16 molar per hour. Similarly, 4 m per hour, we know that manganese 2 plus is 1/3 delta Mn2 plus delta T. So that Mn2 plus delta T is going to be a rate of positive 12 molar per hour. And finally, that 4 m per hour is going to be equal to 1/2 delta MnO4 minus delta T. And so that's going to be 8 m per hour for permanganate. So this is a very easy relationship to get. That's the easy part of this chapter. Finding the rates relative to each other. However, the determining of a reaction rate is an entirely different beast. So we have to figure that out. And how do we figure that out? That is going to be experimental, and as we will see. Now, as we measure the rate, we could easily measure the average rate, but the average rate does not give us a good overall view, because especially if you measure near the end of the reaction is moving incredibly sluggish, incredibly slow, because it's reaching that asymptote where it can't not go any higher, and so it's just going to peter off to almost zero reaction. So what the scientists often want to look at is what's called the instantaneous rate. The rate, essentially the rate at the very beginning where it is going the fastest. And so to do that, we are essentially measuring a tangent to the curve. If you've learned anything about differential calculus, instantaneous rate is basically a differential. You are looking at essentially the rate at the instant of the time where the slope of this line only touches this line very, very briefly. And so we're often looking at the reaction speed only at the very, very beginning at best. So speed typically levels off as so we're measuring just that's essentially the slope right about there before it even gets to 20 seconds. So if we can get any sort of the more instantaneous we can get it, the less of an average, or the average over a lower time scale we can get it, the more accurate we can get the speed. So that's what we try to do. That's what we aim for when we measure these things. That's what we're aiming for when we measure things in lab. The speed, when the time it takes to get to a certain point, but before it slows down to a stopping point. But, so in order to understand these rates, we will work on developing what's called a rate law. Here's where kinetics can throw people for a loop. Well, here and many other places. That a given chemical reaction, the relative rate can depend on multiple different factors of concentrations of reactants. That the reactant concentration can affect the rate, but not all reactants are created equally. In a simple reaction of N2 plus 3H2 goes to NH3, you would expect that hydrogen has a triple effect on the reaction rate, but that's not always the case. Hydrogen may have even greater effect. Hydrogen may have a lower effect. Hydrogen may have no general effect on the rate. And so by measuring the initial concentrations and using that to observe a rate of reaction, we can learn something about how the reaction actually takes place. And so we will write a rate law. Now, this rate law will help us understand what is actually going on, but this must always be determined experimentally. A rate law for a given reaction should look something like this, that rate equals some constant k, which is what we call the little k, called the reaction constant. Now, times a concentration of reactant 1, in this case we're calling reactant A, raised to some power called a reaction order. This is usually an integer value, meaning a whole number value, times reactant B raised to its own specific order. And so generally the larger this integer value is, the greater the effect of this concentration has on the reaction rate. And if we add the orders together, we can get the overall reaction order, whether it's a 0 order, first order, second order, third order, fourth order. It's looking at the overall order, talks about how many collisions need to happen for this reaction to kind of go. Once this collision or bond fragments, the reaction proceeds quickly. So just looking at the experiment I've shown up there, we'll probably look at it more in the next slide, but we have equal concentrations of nitrogen and hydrogen. It has a rate of 3.5. When I decrease the amount of nitrogen, the rate slows down. When I decrease the amount of hydrogen but keep nitrogen the same, the rate stays the same. And when I decrease the amount of nitrogen and hydrogen, the rate goes down. Now, as I said, when we determine the reaction orders and the rate constants, we do not look at the balanced chemical reaction. these often do not directly relate to the coefficients of the balanced chemical equation. That is because the balanced chemical equation looks at the overall reaction and not anything about the mechanism, the how things actually happen. So we're going to look at speeds, and we need to understand how these speeds relate to the order things break. It's like you need to do this before someone can do that. Like if you're doing some sort of you're building a house, before it does, like, to put up the frame, you need someone to put up the frame, then someone can put up the walls, and someone can paint that house and do the electric. If the painting takes a couple hours, but the frame takes a couple days, we're not waiting on the painters, we're waiting on the people to put up the frame of the house. By the time, once someone builds the house frame, the painters go to work. And while the people working on the house frame are working on the next house, the painters have already finished before the frame is up. So we're not ever waiting on the painters, we're waiting on the framers. So that's an example of, like, all these processes are needed to complete a house, but some of them are more important than others. So generally speaking, the general reaction orders usually fall into one of three categories. A zero order, so having an integer value of 0, which means the reaction rate is completely independent of this reactant concentration. It is needed for the reaction to go, but the concentration does not affect how fast it goes. A low concentration goes just as fast as a really high concentration. There's a first order mechanism where this is a direct relationship between concentration and speed. You increase the concentration, the rate increases proportionally. And the other main one is a second order. A second order has a double effect. So every time we increase the concentration, the speed doubles. Every time if we double the concentration, the speed quadruples. That it's essentially a squaring effect. So if I half the concentration, the reaction rate would be quartered. Now, these orders and these rate constants can only be determined experimentally. The easiest way to do this is by varying reactant concentration and then measuring the rate. If you can do that, we can find this rate law. So here is the process we can do mathematically. Given a table of values, we are going to essentially use a system called two equations, two unknowns. We are going to compare two equations together. Technically, we don't know K, we don't know M, we don't know N, but we know A and B. And so when we divide equation 1 by equation 2, or equation 2 by equation 1, it doesn't matter which one we divide. Everything that is held constant will cancel out. K, by its very nature, is constant. And so the K's will cancel out. If I compare two experiments where only the concentration of A changes, then B's will cancel out. So in this particular problem, I'm comparing 5m, 0.5 of molar of A, 0.5 molar of B, to 0.2 molar of A and 0.5 molar of B. The 0.5 molar of B's drop out. The B's drop out. And so we have the rate change has gone from 3.5 to 1.4. This is a simple change of ratio of 2.5. Now, simple exponential rule. If you have two numbers raised to the same exponents, you can put them within the parentheses together and do the math. So, as you see there, that if you have a1 and a2, they're raised to the same exponent, you could take the exponent and extract it outside of that. So you have 2.5 to the n is equal to 2.5. In this case, if I only have three options, 0, 1, and 2, exponent of 1 is necessary to make this relationship true. So it's first order with respect with nitrogen. Now, if the math is ugly, which means if it isn't a nice, obvious number, we have a rule of logarithms. The rule of logarithms says that log of a number raised to an exponent is equal to the exponent out front, so n times log of the number without that exponent. So we can pull that out, and then we can do a simple division. And in this way, we can find out what n is. Now, it just so happens, doing it this way, you get exponent of 1. So it's not particularly hard, but in lab, we may have to use this logarithmic rule. This is different from the natural log, but we can do this all the same. You could do this with a natural log as well. There's a general rule of logarithms and natural logarithms. But that is probably the easiest way to do this. Now, we have one reaction order. Now we should repeat this for another reaction. So we want to find a reaction where the amount of nitrogen does not change to make things easier. And so with that in mind, we can just have it where the nitrogen cancels out. And we look at the concentration of hydrogen changes by 2.5, but the rate has changed by nothing. Now, if we do this, logarithm of 1 is 0. But any number raised to the exponent of 0 is equal to 1. It's a rule of exponents. Any number raised to the exponent of 0 is 1. So the only way to make this relationship hold true is if m is 0. So we have a reaction that is 0 order with respect to hydrogen. Now, with this in mind, we have a generic rate law. Rate equals K times n squared, nitrogen to the first power and hydrogen to the 0th power. Now, in order to find K, all we have to do is plug in any one of our 4 experiments. If this reaction works out nicely, any of our 4 experiments should give us the same K. In an experimental setting where the numbers are not quite so nice, we may actually have to find K with each experiment and then average our Ks. But so it doesn't matter which experiment you use, you should get close enough to the same K unless you have one experiment that is particularly bad. So if I plug this in for the reaction 4, 2.1 molar per second equals K times 0.3 molar. If I divide by 0.3 molar, I get 7. Now the units of K depend on the units that are left over when we've done all of our math. This is another tricky thing. The units of K are present in such a way so that we always get a rate, a molar per second. So in this case, since I only have a first order overall, the units of K is just inverse seconds or 1 over seconds in order for this to give us molar per second. If this was an overall 0 order, K's units would be different. If this is a second order, K's units would be different. If this was a third order overall, K's units would be different. The units of K are just present to give us a reaction rate. As long as I end up with molar per second when all is said and done, that's all we need. That's all you're trying to get. So I think this is the last slide. We'll look at this. We have a reaction A plus B goes to C. Not that we need this, because the rate law doesn't have anything to do with this. So we have A, we have 0.5, 0.3, 0.7, 0.7, 0.3, 0.4. 1.25, 1.47, 2.45, 0.48. Okay. So with that in mind, let's look at the doc cam. Yeah, so so we want to compare reactions where one thing changes. Reaction 1 and 3, B changes and only B, or reaction 2 and 4, once again, just B changes. Reactions 2 and 3, only A changes. That's the only one we can use to find A. Now, there are other ways to find A and B once you've found one of them, but that is a little bit more challenging. I'll show you that as well. But the first thing is, let's set up, we'll just do 1 and 3. We'll look at 1 and 3. It doesn't matter which one you put on top, as long as you relate them in the right way. 2.45 equals K times 0.5 to the M and 0.7 to the N. I'm going to divide this by 1.25 equals K, 0.5 to the M, and 0.5 to the N. That cancels out, that cancels out. So with that in mind, I'm going to solve that first. Yeah, let's sort that out later. 2.45, 1.25, not quite doubled, it's 1.96. And we have 0.7 divided by 0.5, we have 1.4. Obviously, they're not a 1-to-1 comparison. Obviously, this number is not 1, so the good chance this is 2. But we'll just check. The log of the natural log of 1.96 is the natural log of 1.96 is 0.6729, and the natural log of 1.4 is 0.336, let's say 5. So this divided by this, when I take those, would have n is equal to 2. So we got this number. N is equal to 2. Now, I can then compare 2 and 3 to get m. But what happens if I don't have an easy one? What happens if I don't have an easy one? So let's compare. Well, I can't compare 2 and 4. Let's compare 1 and 2. Let's compare 1 and 2. This is a big, foolish extra work. No, but we will do it. We have, so 1.47 equals K A of 0.3 M 0.7 squared. Because since we've already found the n, we can plug this in. K 0.5 to the m over 0.5 squared. So with that in mind, we cannot, the only thing we can cancel out is this. I'm doing the harder step because on purpose, 1.25. And so this gives us 1.176. We have in ratio 0.3 over 0.5 is 0.6 to the m. So since these don't cancel out, I have to evaluate. So 0.7 divided by 0.5 is 1.4, and we square that. I square that, so why would it do that? So 1.4 times 1.4, let's see. And that is 1.96. So with that in mind, let's get this to the other side. 1.176 divided by 1.96 is equal to 0.176 divided by 1.96 is equal to 0.6 to the m. With that in mind, there's a direct relationship of 0.6 and 0.6. So m is equal to 1. I'm kind of running out of room, my own doing. So we have a generic rate law that rate equals K A to the first, B to the second. Now, we are going to plug one of our values in. We'll plug in equation 4 just for giggles. Equation 4, and so our rate 0.48 m over s equals k times 0.3 m times 0.4 m squared. So 0.4 times 0.4 times 0.3 is, so we have 0.48 m over s equals k times 0.048 m cubed. Why m cubed? Because m squared would be m squared is m squared. M squared times m is m cubed. So, solving for k. So 0.48 divided by 0.048 is 10. So k is equal to 10. But the units of k are 1 over m squared s, because 1 over m squared s takes care of 2 of these in the m cubed. And we want to leave one of them behind so that we carry the m through. And the s will need to be there. And so that is the problem. That is our problem. That's where we're going to end this video. That's where we're going to end that video. So I'll just show you that. So our rate law would be this. Rate equals 10 in 1 over m squared s times a to the first times b squared. That is our overall rate law. So we always have to do this by experiment. That's the only way that we can go about it. But once we do it, it doesn't have to be necessarily hard. So you notice on this problem, I did it the easy way. And I used equation 1 to get my k, and it's still the same number. So I just want to show you that all the answers should come up with the same k. Have a good day.